Okay, so Josiah Gibbs, notice I didn't underline his name. You don't need to know his name, but you do need to know what Gibbs free energy is. And it is not Gibbs with an apostrophe. His last name is Gibbs, so don't put an apostrophe in it, okay? Essentially, what he did was he combined enthalpy, entropy, the temperature, everything that spontaneity or thermodynamic favorability is based on into one equation. So he used the equations that we were talking about before and essentially integrated them all into one that tells us all kinds of stuff. Okay, so called negative delta T. Oh, hang on, I'm getting ahead of myself. So he combined and rearranged equations to yield, if we combine all the stuff we were talking about, we get negative of the temperature of delta S of the universe equals, oops, there, I think that's still working, equals negative T delta S of the system plus delta H of the system. Okay, so it takes into account the temperature, the entropy, and the enthalpy. Those are all of the things that play into a process being spontaneous or not. Okay. So what he did is he called negative T delta S, because of the universe, Gibbs free energy. So the temperature and the change in entropy is called Gibbs free energy. And that is essentially the maximum amount of energy available to do work. Okay, so for something to happen. Okay, so if you simplify that to be just delta G instead of negative T delta S of the universe, you get that delta G equals delta H minus T delta S. Okay, so this is our equation. It relates everything we need to know for something to be spontaneous or not. All right, so delta G is the free energy, tells you if it's going to happen or if it's not. Delta H is enthalpy, so that's like our heat, right? Endo versus exo. T is just temperature, and delta S is entropy. So is it positive? Is it negative? So remember I told you that all of these things play into spontaneity, okay? Usually things that are exothermic are spontaneous. It depends on the temperature, right? Especially when you're talking about phase changes. And entropy is usually tends toward being positive, right? That's more spontaneous. So we have to take in all of these things to account to be like, okay, is this whole reaction spontaneous? All right, so the signs can get a little confusing and they are really important. So I'm gonna kind of go over what positive and negative means for each of these values. Okay, and you kind of use this equation to figure out what they're going to mean as long as you know the values mean. Okay, so first, I'm actually going to start with enthalpy because this is from 161, all right? So enthalpy, or delta H, is essentially if it's endothermic or exothermic. If it is positive, that means it required energy. You had to put energy in. This was endothermic if it's positive, and it's exothermic if it's negative. That means energy was released. So either you're putting energy in or you're taking energy out. That's the positive and negative of delta H. Now, if you think about those, which one is usually favored? Exothermic tends to be favored. Okay, like a burning a fire, right? That's a very favored process once you get that spark of energy anyway. It's very favored. So exothermic tends to be favored. Endothermic reactions tend to be not favored, because you've got to put energy or work in order for them to actually work. Okay, now I'm going to move toward entropy. Remember, positive entropy would mean it's going to be more entropic or disordered, right? And we know that that is favored, okay? Because the universe tends toward chaos or more entropy. It's easier to do that. So this is favored. And less entropic, so if it becomes less entropic, because that requires work and it's difficult, entropic, or more ordered, I'm going to put more ordered, that is not favored, not favored, okay? So it actually takes work in order for that to happen. So if I look at my equation up here, I can actually figure out, well, if delta H is favored, so delta H negative is favored. So if this value is negative, I've got a temperature in there, it's never going to be 0 Kelvin. And delta S, let's see, delta S favors positive. So if it was a negative value minus a positive value times a positive value, that overall would be negative. So if everything is favored, delta G is negative when you do your math. So negative delta G means that the process is spontaneous or thermodynamically favored? Spontaneous or favorable. Okay, the opposite is true. Of course, if delta G is positive, if it's positive, it is non-spontaneous, or it is not thermodynamically favored. All right, so that's what all the signs mean. You might want to like earmark this page and come back to it to make sure that you kind of know what's going on with all of the negative and positive values, because you got to kind of keep them straight in order for it to make sense. Okay, so let's bring all these values into an actual real chemical reaction. So I'm going to use graphite reacting with hydrogen to make methane. All right, carbon, hydrogen, methane. Awesome. So I have the delta H of this reaction is negative. Okay, that means it's exothermic. This process is exothermic, which means based on enthalpy, it would be favored. Okay, it has a negative delta S, which means it is going to become less entropic or more ordered, which is not favored. So in order to actually find if the reaction is going to be favored or not, we have to plug those values in to calculate delta G. And if you do that, you get negative 50.5 kilojoules, which means that this process is favored. It's negative. So that means the process is favored, or it is a spontaneous process. Okay. So you have to actually calculate it in this case if you have one thing that's favored and one thing that's not favored to figure out if the process is overall favorable or not. Okay. This is kind of just like a visual for this process happening. We've got the chemical reaction in here. It releases heat. That's what these little squiggly lines. Minimum heat loss of the surroundings is 24.1 kilojoules. This is, and it can do 50.5 kilojoules of work, or those added together essentially have to be 74.6. So it loses heat, or it can get do work. And then, so that's the negative delta H of the reaction, but it also has a negative delta S because it becomes more ordered, right? I've got two gas particles on the left and only one on the right. So negative delta S. So when we actually calculate it, then it is favored. So this reaction does happen spontaneously, and that's essentially what the question is asking. Okay, so that is one way to calculate delta G. We are actually going to talk about a multitude of ways to calculate delta G. One is this equation here, okay? Another is by using delta G values that you can look up on that appendix that I have attached that you need to print. This is actually very easy. It's just like our delta H or our delta S summation reactions. Delta G naught, remember that means 25 degrees Celsius in 1 atmosphere, is equal to the sum of N times G naught F, that I'll talk about what that F means in a second, of the products. Okay, again, it is products minus the reactant, sum of N G naught F of the reactants. Okay, exact same equation, products minus reactants. Okay, so if I look up delta G, notice these are delta G F's. That means formation. Okay, so that's essentially the spontaneity of creating something from its pure elements. We talked about this in 161 with delta H, that delta HF, delta H formation, is the amount of enthalpy associated with creating something from its pure elements. Delta G is the spontaneity of that reaction from its pure elements. Okay, so you can look these up and then we can calculate delta G for a, let's put reaction here, for a reaction. So in example number 6, I want you to determine delta G for the following reactions using thermodynamic data. Okay, that means looking up the formations. What do they tell you? So essentially I'm asking, is it favorable or is it not? So try to calculate delta G by looking up the values for each of these reactions and figuring out if it's favorable or if it's not. Okay, so here's the math for both of these processes. I've got delta G of the reaction for the first one ends up being negative 24.7 kilojoules per mole. Negative means it's favorable. And delta G for the second reaction is 1,143 kilojoules per mole, which means that this reaction is not favorable. That's again taking into account enthalpy and entropy. That's what delta G does. So that was a second way to calculate delta G.